Okay, so right now we are in the week 9 of the Introduction to Material Science and Engineering courses. And let's start with the today's discussion. And these are the list of the topic that has been covered till now. So we first discuss about the phase transformations, mostly about the solid, liquid, and gases. And among the solid, we saw that how the solid state transformation can also be there. So they can change from one to another. Next, we went to the nucleation, capillary rise. We saw that how the capillary rise and the nucleation both are governed by the surface energy. The reduction of the surface energy is the one which is leading to this, and they have the similar analogy. So they have studied on the surface energy. Then we talk about the nucleation, growth, and overall transformations. And after this entire transformation part is over, we saw that how the TDT diagram will be. So one of the limitations of the phase diagram that it doesn't take the factor of time into account, but which has been covered in the time temperature transformation diagram. Later on, we saw that what is a homogeneous nucleation and heterogeneous nucleation. More or less, we know that homogeneous nucleation takes place within the material, inside it, while heterogeneous take place at some certain particular sites. It can be the site can be surface, site can be grain boundary, it can be any defect. You can also say that if we add an impurity, this impurity itself can act as a nucleating site, and this will lead to the formation of the this will lead to the heterogeneous nucleation. Then in depth we discuss about the heat treatment of the steel. We discuss about the annealing, normalizing, quenching, or stamping. Those stuff we have been covered. Then on a major scale we learn about the TTT diagram for the ejector steel. So these are the list of the content that has been covered in the week 9. If there is any doubt in this particular week, you can let me know. And also you can comment on the video, or you can post your question on the doubt solving forum. We will definitely respond to that. Let's go ahead, let's try to solve few questions based on the content that has been covered in this particular week. These are the list of the process in the column A, and the column B are telling about that what are the name of the particular transformations. So for example, say liquid to gas. So we are evaporating. Liquid to gas transformation is nothing but evaporation. So option B it will match. Gas to liquid. So the reverse process. The reverse process is a condensation. Solid to liquid. Solid to liquid, we know if I take ice, if I try to heat it, it will become water. The process is a melting. And liquid to solid, we know that it's nothing but a freezing. So this is how we have solved it. So 1, 2, 3 and 4. They are going to match with B, C, D and A. Let's move ahead. Let's go to the question number 2. Let's move to the next question, question number 2. So true and false based. Let's go with the first one. A phase transformation is a thermodynamically feasible only if the final phase has a higher energy than the initial phase. So they are telling that gives free energy for the final should be higher than gives free energy for the initial. Then only the transformation will be the thermodynamically feasible. And we know this is not the case. That the product should be more stable. So the feasibility will happen only if The initial phase is having the more Gibbs energy than the final phase. This is where the thermodynamic feasibility will lie. So we can say that this option is false. Let's go to the next question. The driving force for the transformation is zero at the melting point. We saw that, let us say this is a temperature and this is a Gibbs energy axis. Let us say this is a melting point. This is solid graph and this is a liquid graph. Solid, liquid. We know at the melting point, the delta G of liquid and the delta G of solid, sorry, the Gibbs energy of the liquid and the Gibbs energy of the solid, they are equal. Sorry, pardon. The Gibbs energy of the liquid and Gibbs energy of the solids are equal, and so we can say their difference, solid to liquid or liquid to solid, will be nothing but zero. So at the melting point, the driving force for the phase transformation, delta G is a driving force. So it will be the zero. So this answer is, this option is, sorry, it's true. Let's move ahead. The driving force for freezing decrease with increase in the undercooling. Freezing. Freezing is a transformation where liquid convert to the solid. So the driving force, the delta G for this will be the delta G for this transformation, delta G for the freezing will be the product, the delta G of the product, that is the solid, minus delta G of the liquid. When this will be the maximum, like when, under what condition it will increase. Undercooling they are talking about, let's see. This is liquid, this is solid. This is the melting point, temperature axis, and this is the Gibbs energy axis. We can see that at the melting point it is zero, that solid to liquid, sorry, liquid to solid transformation. But once I keep on decreasing the temperature, when the temperature I am going to the left side, that is, once I keep on decreasing, once I keep undercooling, this driving force, the delta G, this is keep on increasing. So we can say that if more is undercooling, if undercooling is increasing, this delta T, which is temperature at which transformation is occurring, and minus the melting point. If this is increasing, it means that the delta G will also increase. The driving force will also increase, and so undercooling, the driving force or the freezing decreases. So they are telling that the driving force is decreases with the increase in the undercooling, which is incorrect. We know that right now with this discussion we got to know that as the undercooling is keep on increasing, the driving force, the delta G, is also increasing. So option, this one is a false. So false, true, and again false. This is how we have solved this question. Let's move ahead to the question number 3. If there is any doubt in this question, please feel free to contact us. Very easy. This question number 3. What is the thermodynamic driving force for the phase transformation? Driving force for the phase transformation. Let us say a phase 1 has transformed to the phase 2. What is the driving force for this to happen? We know that it's the Gibbs energy of phase 2 minus Gibbs energy of phase 1. This is the driving force for any particular phase transformation to occur. So we can say that option B is the right answer over here. It's not the temperature, it's not the pressure, it's not the volume. It's the delta G. Let's move ahead. So now what is the first stage of the phase transformation? Like how the phase transformation occur? What is the first state of it? We know that for any phase transformation to occur, the process, the nuclei should form. And the formation of the nuclei take place by something known as, by the process known as nucleation. And this form nucleation, the nuclei, it will grow then, the process of growth will occur. And with this, any transformation can take place. Whether it's a liquid to solid, solid to liquid, or any solid state transformation that we have learned, that will happen over here. So solidification is a process, no. So it's not the it's not the stage of the phase transformation. Melting is again the process. Growth is a second step, second stage. Nucleation is the first stage. First nucleation will occur, then growth will take place. Question is asking, what is the first stage of the phase transformation? So option B is the right answer. Let's move ahead to the next question, question number 5. What is the critical radius in nucleation? So they're not asking about the formula, they're asking what this particular thing signifies. So let us say R star is a critical nucleation, critical radius. Let us say this is a case number 2, the case number 1, where R is less than R star. Case number 3, where R star, where R is greater than R star. So in the case 1, what will happen that since the size is low, it can again dissolve, it can dissolve back, or it can grow, anything can happen. For this, for R, which is greater than R star, in this case, a growth has taken place over the nuclei, over this nucleation. So this is a case where it can dissolve also. This is a case where it will grow further. So the radius at which the free energy change is minimum. The radius at which the free energy change is maximum. The radius at which the free energy change is 0. The radius at which the surface energy is 0. So what do you think? So we have learned that in the class that if we try to draw the free energy delta G with a radius, there is a two factor. One is the surface and another is the volume. The surface factor will go like this and the volume factor will go like this. Their resultant, the overall, will go something like this. We call this particular point, this particular radius at the R star, because after this the delta G is keep on decreasing. Well, before this, like if we say, let's say we're starting with a 0, we are keeping the R star, the nuclei started forming. This nuclei over here, it can go in the forward and also it can go in the backward, but the tendency to go in the backward is more because here the Gibbs energy will keep on decreasing. R star, after R star has formed, all the nuclei will start again. The nucleation process, the stable nuclei has formed, the critical radius has been reached, and so the growth will take place. So we can say that R star is the one which is a desired to us. Also the factor that the delta G over here is maximum. For this entire curve, this entire black curve, we can say that over here delta G is maximum. So we got two things from this question, that what is R star, that is it's a stable nuclear radius above which a growth will take place, and delta G is the maximum at that particular ashram. So we can see that the right answer will be the option B. Let's move ahead to the next question, question number 6. What happens if the radius of the nucleus is less than the critical radius? So now the same thing they are asking that. We made a diagram. Here we made a R. It's a delta G. Here it will go in the straight line. Be like this. This is a surface. This is a volume. The resultant will go something like this. This is what we call R star. And we knew that below R star, let's say this particular point, a nuclei can grow, it can dissolve also. What will happen to the radius of the nucleus if less than the critical? The nucleus will grow. We cannot say this thoroughly. The nucleus will dissolve, the free energy will decrease, the free energy will increase. So here we can say that it has a possibility that it can dissolve. So the nucleus will dissolve over here. So for this particular, the right answer will be the option B. Let's go to the question number 7. It's a Melzer pair type. Nucleation, growth, critical radius, and the surface energy we have to match. Both. The nucleation, increase in the size of the nuclei, initial formation of the new phase, radius at which the free energy changes minimum, and the energy associated with solid to liquid transformation. The nucleation, we know it, like if the nucleus is taking place, it means that the increase in the size of the nuclei, the formation of the new phases. So here, the nucleation signifies that the initial formation of a new phase. So first one is going to match with the option B. The growth. Growth is the increase in the size of the nucleus. That is option A. Critical radius. The radius at which the free energy change is maximum. Free energy change, that is a delta G. This is maximum. So we can say that C3 is going to match with C. And only this one is left. Surface energy, the energy associated with the solid liquid interface. We can say that if the transformation is a solid to liquid, so the interface at which it's happening that's surface energy. The surface at which it is happening, it's surface energy. So we can say that it will be the option D. Let's move to the next question. What is the driving force in the capillary rises? We saw about this regarding the capillary rise, that how this and the nucleation process are more or less same, like this, governed by the same energy. So we know that the additional energy, the energy due to which this capillary rise is happening, is nothing but a surface energy. And so in the test tube we saw that a liquid will rise in this particular test tube, so that it can cover this particular additional surface area and release that particular energy. Surface energy will be released. With that we have solved this question. Okay, so correct. Question number 8. Let's move to the next question. Question number 9. So now this is the true and false side question. Yeah. Question number 1. The critical radius R star is in nucleus and correspond to the minimum in the free energy. We found that it's a false. Instead it corresponds to the maximum. The opposing force in the capillary rise is the volume free energy. Again, it's a false. The correct answer will be the, instead of volume, it should be the surface. Let's move ahead. The surface energy term in the nucleation is proportional to the R cube. No, it's not the case. It's a volume energy term which is proportional to the R cube. Volume is proportional to the R cube. While if we talk about the surface, it is proportional to the R square. So again, this one is false. So all the answers are false here. Let's move ahead to the next question, question number 10. So what is the unit of the nucleation rate? Is it meter per second, per meter cube per second, meters cube per second? Meter per second, per meter cube per second, second, or meter cube per second. And we know that it's a number of nuclei that has been formed per unit volume per unit time. So the option B will be the right answer. Now let's see the what about the unit of the growth. A nuclei has formed over here. Now it's growing in the particular direction, let's say. Now this much growth has been occurred. So how much distance of growth has happened in a second? That is the growth rate. So we can say that the option A, that is meter per second. How much growth takes place in a second? This is the growth rate. So option A is the right answer. Let's move ahead to the question number 12. At what temperature the nucleation rate is 0? So here we have saw that if I'm talking about the nucleation rate, let's say this is the temperature, and the transformation still, let's say solid to liquid to solid. The growth rate, sorry, the nucleation rate will follow this particular type of curve, where this one is the melting point and this is a 0. So here the two answers are correct, and the nucleation rate, the nucleation rate at design, it is 0 when at this particular temperature. When the temperature is very low, like close to the absolute 0, or the temperature is high, that is close to the melting point. At this particular time period, the nucleation rates are 0. Okay, so with that, question number 12 we have solved it. Let's move ahead to the question number 13. This question is telling that what is the relation between the temperature of the maximum growth rate, sorry, nucleation rate, and the temperature of the maximum growth rate. We saw that in the blue curve, let's say I'm making the nucleation rate, and in the red, sorry, in the black, I'm making the growth rate. We know that this is a growth rate and this is a nucleation rate. We know that the temperature at which the maximum growth, the growth rate will be higher, will be more than the temperature at which the nucleation will be high. Okay, maximum they are talking about. This is a maximum. So the right answer will be the option B. Let's move on to the next question, question number 14. What is the shape of the curve for the fractal transformation as a function of the time? With the time fraction transformation, if we have to draw, it will look something like this. So it will take it's more or less like a S. So it's a S say sigmoidal curve. Question number 15. Now, what is the primary reason for the initial slow rate of transformation? High atomic mobility, high nucleation rate, low number of nuclei, low growth, low growth rate. Let's say I'm having the I'm having the liquid. Now, initially, the driving force for the nucleation to occur will be the low, because now right now the temperature is Tm, melting point. If the temperature is decreased little bit with respect to the melting point, then the nucleation will occur. And when this nucleation occur, give me the red one. Then only the transformation will begin. But we know near to the melting point, near to this transformation temperature, the nucleation rate are very low. And since the nucleation rate are low, the number of nuclei are low, and due to which the transformation is slow. Let's move to the next question, question number 16. What causes the slowdown of the overall transformation rate toward the end of the transformation? So here, like we have seen the S curve, the fraction transformation curve, which is something like this. Where we can see that the transformation, uh, like the transformation rate near to the end, is quite slow. It's taking a lot of time. The fraction of the time to transform is very high. While here, if we say the transformation time is quite high. Sorry, transformation time is very low. Here it's very high, here it's very low for this particular transformation to occur. So now why is it that? Why it is the case? It is because of the impingement of the particle which we have saw in the class. Okay, once the growth has occurred, one particle is over here, now second particle is somewhere over here. Now the particle number 1 won't let the particle number 2 grow because they are impinging with each other. They won't allow the growth of each other to happen. So the option C here is the right answer. Since the growth is restricted, the fraction transformation, the impingement which is happening will impingement will be more and the fraction of transformation will be less, and the transformation is very sluggish. It will slow down at the end. Let's move toward the next question, question number 17. What is the nose of the TTD curve represent? We have seen the TTD curve, time temperature transformation. It is more or less something like this. So now what this particular nose, this is representing? The maximum transformation rate, the minimum transformation rate, the start of the transformation, the end of the transformation. We have saw that if you talk about the rate at which the transformation is happening corresponding to this, it will be more or less like this. Over here, the maximum rate is the one which is corresponding to the nose of the transformation. So the transformation rate at the nose will be the maximum. So option A is the right answer. Let's move ahead. Let's go to the next question, question number 18. What is the result of very fast quenching in the time temperature TTT diagram? if we are if we are cooling it very fast, like if we are bypassing the, this is our curve. Let us say we started somewhere from here and we are quenching it very fast. What will happen? The transformation will be like, it will be very fine. It will be so fine. One can also say that the finer grain is okay, one thing, but since we are going for the quenching, the transformation will be the glass transformations. It won't have much time. Uh, the liquid will not have much time to transform to the solid, and it will take the amorphous shape itself, the shape which was there in the liquid, that same shape will be retained, and so the transformation, it will lead to the formation of the glass. That this particular process, very fast cooling, will lead to the formation of the glass. If we talk about the metals, it will lead to the formation of the metallic glass. Question number 19. Okay, let's now we have to do this match the following. If the cooling process is slow, it will lead to the like very slow cooling process, so it will have a sufficient enough time for the growth to occur. So we can say the coasting will take place. While for the fast cooling, the fine grain structure will occur, and the quenching, we knew that the glass formation. So option will be the B, A, and C. One. Let's move ahead to the next question, question number 20. Now, very interesting question. What is the key difference between the homogeneous and the heterogeneous nucleation? Homogeneous nucleation occur on the surface while the heterogeneous occur in the bulk. Homogeneous nucleation occur in the bulk while the heterogeneous nucleation occur on the surface. Homogeneous nucleation is faster than the heterogeneous nucleation. Heterogeneous nucleation required more energy than the homogeneous nucleation. See, a heterogeneous nucleation occur when occur near to the defects. A defect can be surface, it can be near any nucleating site, addition of any impurities, or the within like the grain boundary, that is also a defect. And it's happening because the energy there required is lower. The defect will have some certain amount of energy itself, and so the nucleation will occur over there because of that a particular additional energy. Okay, so now here we can say that the heterogeneous required more energy. No, it's incorrect. Heterogeneous required less energy. Homogeneous nucleation is faster than the heterogeneous nucleation. Again, it's incorrect because heterogeneous nucleation is the one which is requiring the less energy, and it is quite faster. So here will be slower. Homogeneous nucleation occur in the bulk. This is the right one. Homogeneous will occur in the bulk, while the heterogeneous nucleation occur on the surface. So option B is the right answer. Option A is just opposite of option B, so it's incorrect. Let's move to the next question, question number 21. Again, what is the shape of the nucleus in the heterogeneous nucleation? So this is the surface, a liquid has been formed, the nuclear growth take place, and it will lead to the something like this is a gas, solid, liquid phase, or we can say liquid solid transformation. Anything is happening. So the shape will be the spherical cap. Let's go to the next question, 22. What is the relation between the critical radius for the homogeneous and heterogeneous nucleation? They are talking about the R star for the homogeneous and the R star for the heterogeneous. When we talk about the critical radius, uh, delta G and R, So here we can say that here we saw that there was no discussion about the homogeneous and heterogeneous. Like they are independent of the nucleating site, the site at which. So the process of nucleation, whether it's happening by homogeneous nucleation or whether it's happening by the heterogeneous, it's not going to affect the critical radius. So in the both the cases, this R star will remain unaffected. So the here we can say that option C will be the right answer. They will be exactly equal with each other. Let's move ahead to the next question, question number 23. What is the microstructure is associated with the lowest hardness in the lecture? Like we discussed about the perlite, fine perlite, coarse perlite, bainite, and martensite. We have saw that the microstructure where we have obtained the highest, where we have obtained the more grain size, the grain size is higher. That is a coarser one. Is the one which is having the lowest hardness. So that as the grain size increases, the hardness value decrease. So fine grain size will be the like more hardness, while the coarser one will be having the low hardness. So among this, the fine perlite and the coarse perlite, we know that the coarse perlite with the one with having the lowest hardness. Bainite is something which we obtained comparatively high cooling rate. Cooling rate is higher, so growth rate will be the low, and so the finer microstructure will form. Martensite is the hardest one. It's not the slow. It's not the lowest. So 23, the right answer is option B. Let's move ahead. Which heat treatment produced the which heat treatment process involve heating the steel after quenching to reduce the brittleness? We quench, we form the outer quenching. What we got, we will get the martensite. Now to decrease its brittleness, it's very brittle. Now to decrease this brittleness, what we'll do, there is a the heat treatment process known as the tempering is take place. Tempering is a process where we heat the particular martensite steel to little comparatively higher temperature and hold there for the couple of time, which will lead to the decrease of the brittleness. So the right answer is option C. Let's move ahead. Let's go to the next question, question number 25. What is the primary limitations of the iron-carbon phase diagram in the understanding the phase transformations? Iron-carbon phase diagram. So we are talking about the phase diagrams. And we know the one of the major limitation is the time factor, which is not included. So let's see what is the it like the time scale. Still, let's read the other options. It does not include the carbon concentration. No, it does include. It does not show the temperature variation. Temperature variation is there. It does not include the austenite. No, it includes the austenite also. So A, C, and D are the incorrect. Right answer is option B. Let's move ahead to the next question, question number 26. What is the primary factor that determines the coarseness or the fineness of the perlite? So you have the steel with you. You want to make it coarse and you want to make it fine. What factor will affect it? We know that if I cool things very fast, I will produce the fine microstructure. If I cool things very slow, then I will produce the coarse microstructure. So it all depends upon the cooling rate. So if I have a steel at a high temperature, let's say I have austenite with me, I heated it. Now someone is telling that give me the steel with the low hardness. I don't want the high hardness to it. So what I will do, I will do the annealing. I will cool it very slowly. I will get the low hardness steel. While the other guy is telling that I want someone with a very high hardness. The steel should be very hard. So in that case, I will do the quenching. I will cool it very fast. Okay. Normalizing is also one of the process which one can follow. So the major, the primary factor over here is the cooling rate. Okay. Let's move ahead. Question number 27. What is the primary reason for the C-shaped curve in the TTT diagram? Why the C-shaped curve is there? The balance between the driving force and the atomic mobility, the balance between the temperature and the time, the balance between the carbon concentration and the time, the balance between the nucleus and the growth rate. So the major factor, let's see how this has came. It came like the time temperature transformation. We have saw that it depend upon the nucleation and the nucleation rate and the growth rate. Where the transformation rate is highest, it corresponds to the nose. Transformation rate is low, it corresponds to this particular points. Right. And from where this particular curve came, okay, this is the transformation rate, nucleation rate growth rate, or you can say that dx over dt, and this is the temperature. From where this graph has came, it is associated with the nucleation and growth. Thinking in this way is incorrect. Now we have to think even further. The nucleation and the growth. Let's say any of them. Like because for the nucleation also the same shape form, for the growth also the same shape form. What is the drive? What is the factor like why this particular shape has formed for the nucleation and the growth? It is because let's talk about the only the nucleation to occur. So at the high temperature, the nucleation will not occur because the driving force for the nucleation is very low. Delta G is very low. While let us say someone went to the very down, here also they are telling that the nucleation is not, sorry, the nucleation is not taking place. The reason for it not occurring because the driving force is quite high. But the nucleation to occur, the clusters of atoms should come together. And for the cluster of atoms to come together, the diffusivity should be there. That is, atomic mobility should be there, which is not over here. So somewhere in between, where the driving force, that is delta G, is also sufficient, and the temperature is also sufficient enough that the atomic mobility is high comparatively. So in that way, we can say that like that is the reason why this particular C shape has been formed. So here the competition is between the driving force and the atomic mobility. So the balance between this and this is what leading to the C shape curve formation. So for this 27, the right answer is option A. Temperature and time, no. Carbon concentration, temperature, no. Nucleation and growth, no. Option A is the right answer. Let's move ahead to the next question, the final one. 28. True and false. Okay. The transformation time decrease as the temperature decrease below the eutectoid temperature. The transformation time decrease as the temperature decreases below the eutectoid temperature. This is correct. Let's say this is our eutectoid temperature, 725 degrees Celsius, from where this butter shape has been formed. So this is a transformation time, and this is the temperature. So as the temperature is keep on decreasing, the transformation time is also decreasing. So this is the right answer. The driving force for the transformation of austenite to perlite is the increase in the surface energy. No, it's a decrease in the volume energy. So it's incorrect, so it will be false. Uh, the primary factor that determine the coarseness or the fineness of the perlite is the cooling rate. That's right, it's a true. We have discussed about this. The TTT diagram is used to understand the time required for the phase transformations. That is also correct. So the time factor which was missing in the phase diagram has been covered by the time temperature transformation diagram, TTD diagram. And yeah, so with that we have covered this entire this week questions. This is question number 28. I'll display one by one. 27, where we discuss about the C shape in the TTD curve. Under what condition fine and the coarse sneak can occur? Fine perlite and coarse perlite one will get. Then we discuss about that what is the lagging in the phase diagram. Then the heat treatment in the steel, like how to decrease the brittleness of the martensite, how one can get the finest lowest hardness. Is the critical radius is affected by the nucleation process, whether it's happening by the nucleation is happening by the homogeneous or heterogeneous. What is the shape of the nuclei which is formed in the heterogeneous? What is the difference between the homogeneous and heterogeneous nucleation? Then again the effect of the cooling rate on the microstructure we have saw. Under what condition a glass formation can take place. Then here we discuss about the norms of the TTD curve, the rate, the point, the temperature at which the maximum transformation rate obtained. Then the fraction transformation which we have obtained, that like okay, what is the one which is impinging, why the transformation rate is very slow at the end of the transformations. And then we discuss about why the nucleation rate is very slow initially. What is the curve of the transformation, fractional transformations. And then we talk about the temperature at which the maximum nucleation and maximum growth rate is obtained, and what is the more or less rough relation between them. Here we discuss that at what temperature the nucleation rate will be 0. What is the unit of the growth? What is the unit of the nucleation rate? Few questions we discuss upon based on the critical radius of the nuclei. We saw the analogy between the capillary rise and the nucleation, and what is the energy that govern these things to occur. Again, the more or less same things. What will happen if the radius is smaller than the critical radius? What is the the delta G at the nucleation, at the critical radius of the nucleation? And in the phase transformation, which one is the first, whether the nucleation is the first or the growth is the first. And then we talk about the general transformations, like what is the driving force for any transformation to occur. And then we talk about the thermodynamic feasibility and how the undercooling will affect the transformations. And then we did this particular transformations matching, and these are the list of the content that has been covered in this particular week. So with that, our week 9 content has been over. I will again encourage you guys, if you have any doubt in this particular week or any doubt in this particular doubt solving session, you can please feel free to contact us. You can text on the dot solving forum. You can also text on the comment on this particular video if you are facing any issue. We'll definitely respond to that. Okay, with that, let's meet up in the next week, week 10, in the upcoming Saturday. Okay guys, bye bye.